Okay, so get back to the questions. We know that the main function for a chromatography is to separate different types of compounds or different compounds. So how did this happen? Well, basically it's similar to what we have in SPE. Do you guys still remember the solid phase extraction? So solid phase extraction is pretty similar to chromatography, except that the the whole purpose of using SPE cartridge is to retain as much as possible for the target analytes. But in the case of chromatography, we don't want to retain them. We want to separate them based on different affinity for compounds and your stationary phase. So in a chromatography, let's say this is column, and then inside the column you have a solid material. And again, when the samples, let's say this is a mixture, you've got 5 compounds, compound A, B, C, D, E. You have 5 compounds. And by gravity, this mixture is falling downwards. And when this mixture is falling through the packing material, let's take a closer view. So this is a packing material, and on the surface, it might contain a different functional group. So let's say one of the most commonly seen is C18. It has 18 carbon. So for a functional group containing 18 carbons, it features pretty hydrophobic nature, right? So it's a C18H38, for example. So it's pretty hydrophobic. So when the compound is flowing through the solid bits, let's say it's a solid bits, the compound is going to interact with the functional group. Okay, so somehow compounds with a higher hydrophobicity would be dragged down by this sort of interaction. Okay, for compounds without like a high hydrophobicity, it might pass through the bits very quickly. So that's the reason why these 5 different compounds can be separated when they are flowing downwards. Okay, does it make sense? It's simply based on the molecular interaction between your compound and the functional group on the surface of your packing material. So packing material here is the solids or stationary phase. We call it stationary phase. Stationary phase 就是固定向的意思哦，它就是待在这个管柱里面不会动的。So on the contrary, we have a stationary phase, and we also have a mobile phase. Mobile phase. So mobile phase is the phase that's moving in a system. But we'll come back to talk about mobile phase later. So simply put, you load the sample. You load the sample, and then you supply it with a stream of water. Okay, so you just keep pumping water into it. So the water is like the driving force rather than the gravity. I mean, if you pump water through the column, and then the column, the water is keep moving those compounds, like moving forwards. And because of the molecular interaction of compounds and the stationary phase functional group, eventually they got separated. Okay, so that's how the working principle. Right? So we say that there are 2 phases in a chromatography. The first one is a stationary phase. So in the case of this column, it's the bits or anything that is solids packed inside. It's not moving; it stays later. Whereas the other moves in the direction is mobile phase, mobile phase. So in this case, it's the water. So you, after loading the mixture of compounds, you supply it with a stream of water, and the water is going to drive everything moving towards downwards. Okay, so all chromatography analysis are based on the establishments of equilibrium between a stationary phase and a mobile phase. So what does it mean? What does it mean here? So to separate the compounds, it's basically based on the establishment of equilibrium between stationary phase and mobile phase. So that basically means that, imagine that you have compound, a mixture of compound here, and when the compound is flowing through the column, like the compound have different affinity towards to stationary phase. At the same time, the compound also have different affinity toward the mobile phase. Okay, so the mobile phase in this case is water, and the stationary phase here, I don't know exactly what is inside, but let's take a C18 column as an example. So C18 column, it has long carbon chain on the surface. Okay, so compound A, B, C, D, E would have different affinity towards the C18 surface, and at the same time also have different surface with the water phase, right? So let's say for compound A, let's say it's toluene or toluene, and compound B, let's say is aniline or aniline. So when the mixture, okay, so you have water as a mobile phase. So when the mixture of compound A and B is flowing through the column, what would you expect? Which one is moving faster? Is it toluene or is it aniline? Which one is moving faster than the other one? Aniline is moving faster than the other one. Okay, that's probably correct. That's because we'll expect that both of the, in both compounds, the aromatic ring has like high affinity with the C18, but the NH2 functional group is more polar than the methyl functional group. Okay, this one is more polar. The functional group here is more polar. It's NH2. If you check the electronegativity in the table, periodic table, you will see that the electronegativity is the differences in N and H is much larger than CH. So this one is more polar. The polar means, polar functional group means that the interaction with water is gonna be stronger. Okay, so this compound has a high affinity with the water phase. So when the water is flowing down, it goes with the water. So that's the reason why aniline is flowing like faster. Okay. And if we use another like stationary phase, they say instead of C18, it's like a C8, and then with COOH, CO functional group or COH functional group, polar functional group here. So again, the polar functional group is going to provide additional interaction site with the polar functional group. So in this case, if you are using this kind of stationary phase, the aniline might be moving like a bit slower than volume. Okay, so the separation occurs because of the intermolecular interaction between stationary phase and the compounds. That's the key takeaways. Okay, so come back to the question, at the very beginning, why I ask you guys, why do we need to do separation before we can quantify them? Well, one of the example would be, let's say we use a UV-vis spectrometer. We know that UV-vis spectrometer can be used to like quantify the concentration, right, of a compound. So this is a sample cell, and okay, if the sample contains it has only one like a compound inside. So we know that the absorbance is proportional to the molar absorption coefficient of your compound and the light path length and the concentration of your compound, right? That's Beer-Lambert's law, or the absorbance you have from the machine. You got from the machine. Absorbance is proportional to the concentration of your compound. Okay, so that's when you have a single compound. After obtaining the absorbance, you can directly link to the concentration. However, in our environment samples, usually contains more than one compounds, right? It contains like a whole lot of junks apart from your target analytes. So we have compound A, B, C, D, E, all the way to like compound Z. So many different compounds in a mixture. So, well, you don't exactly know what's inside, right? So can you measure the absorbance and then use this equation to quantify the concentration of target analytes if you are not separating your target compound from the interference? That's not possible, right? So that's the reason why we need to separate before we can do the quantification. Okay， 好，所以这边重点就是说，这个通常我们在定量的时候，很多机器都是根据就是你单一个样品的话没有问题，单一个compound在里面的话没有问题。可是环境样品里面，它最头痛的地方就是它成分很复杂，你永远不知道里面有什么东西。OK， 所以为什么要分离的原因，是因为就是分离完之后，你才有办法用机器去就是一个一个去测它的讯号，然后把它转换成浓度。那如果以这个 UV spectrometer 来做例子的话，环境样品在里面，一个环境样品你是没有办法直接透过吸光度来求得某一个 compound 的特定浓度因为你会不知道其他的 contribution 比方说the other compounds and then light path, the concentration of other compounds. You don't know what's inside, so you don't know what the contribution from the other interference on the total absorbance. Okay, so that's the reason why we need to do separation before analysis. Okay, so key points to separate compounds. That's the main function of using chromatography. All right. So in these chapters, I'll be introducing three commonly used chromatographies, including gas chromatographies, liquid chromatographies, and ion chromatographies. So for liquid chromatographies, usually we use high-performance liquid chromatography instead of the conventional liquid chromatography. So the main differences between conventional liquid chromatography and the high-performance liquid chromatography is that in the case of HPLC, it has been specially designed to be able to tolerate high pressure. So being able to tolerate of high pressure means that you can operate under like a much higher flow rates. So it gives you a higher performance. 讲的有点快那个 HPLC 它跟传统的 LC 最大的不同那个我其实没有看过传统的 LC 但 HPLC 呢，它就是这个管子呢，你所用的管子都比较坚韧一点，比较坚强一点，然后它的这个 chamber 耐受压力的程度比较厉害，所以这个时候是怎样呢？你就可以 用大一点压力去挤这台机器，让它跑快一点。不然你做这个分离的话，通常要分离很久。所以 HPLC 跟传统的 LC 最大的不同就是 HPLC 它可以在承受比较高的压力这样子。Okay. So the third one, ion chromatography is a special case of a liquid chromatography. So you may consider ion chromatography a special case of liquid chromatography. 我看到 need to slow down my pace. 我好像讲太快了，有点累，休息一下。Oh, so by the way, next week we don't have an in-person class here. So as I say, I have a conference. So I'm offering like a previously recorded videos next week, and the following weeks I'll be on a business trip. So, but at the same time, you guys have a technical tour, right? Are you guys all going? 大家有要去那个technical tour 吗？就是要去那个 ，right? And then the class would resume in the following weeks. In the following week. All right. So get back to ion chromatography. So in the case of ion chromatography, we use ion chromatography to separate ions. So the main function of ion chromatography is to quantify the concentration of ions, including the cation and anion. For example, carbonates and chloride, those are examples for anions. Or ammonia, sodium, potassium, they are examples of cations, right? And as you may see later in these chapters, the configuration for ion chromatography is pretty similar to what we have in liquid chromatography. So generally speaking, it's a special case for a liquid chromatography. Okay, so get back to gas chromatography, or GC. So GC, the separation of GC is based mainly on the partitioning between a gas mobile phase and a liquid stationary phase. So imagine that in the case of gas chromatography, you have a column, okay? And when after injecting your sample into the machine, okay, remember in the case of GC, the sample should be in gaseous phase, And when the gaseous phase compounds, is moving through the column, the compound somehow interacts with the stationary phase. And this stationary phase is actually a really thin film, liquid stationary phase. It's in liquids. So for GC, sometimes we call it gas liquid chromatography. Sometimes we call it gas liquid chromatography. Okay, so okay, so imagine that this is a gas chromatography column for gas chromatography. It's like a cross-section view. So inside the column, you have a thin film. So this is the thin film stationary phase. And it's liquid. So it's actually pretty sticky. It's pretty sticky. 它是很浓的那种意象去想象一下。 It's pretty sticky. And, the surface of the thin film stationary phase would, attach with a spatial functional group. Spatial functional group. I'll show you guys an example later. But, on the surface, it has some functional group. Okay, functional group. And when your compound, let's say benzene, and then like toluene or chlorobenzene, those are compounds with low boiling points. They are ready to evaporate. Okay, so those compounds, got injected into the machine when they passing through the column. The compound somehow interact with the functional group on the surface. Okay, so eventually they got separated. Right? You guys know what I'm talking about, right? So, question here. What is the main driving force for moving everything, like moving forward? What is the driving force for allowing everything to move forwards? In previous case, when we are talking about the traditional column, separation column, we introduce water as the mobile phase. And water is push everything to move forwards. How about gas chromatography? What is the main driving force? 就是大家在 GC 的话，大家想一下嘛，那你总不可能就是摆在那边，然后康胖就自己往前跑了吧？Yes. So in the case of gas chromatography, usually we apply a stream of gas. Usually it's a nitrogen gas. So, in the case of gas chromatography, usually it comes with a gas tank alongside. So, the machine gas chromatography is connected to a cylinder of a gas, and the gas, the most commonly used would be either nitrogen or helium. Helium. They are inert to basically everything. So, and the reason why we are using nitrogen or helium is because we are expecting little interaction, little reaction between the gas and the compound. If you are using a pretty reactive compound, it doesn't make any sense, right? You are using like a nitro oxide or something, which is reactive with your compound, then doesn't make any sense. Okay. So what about liquid chromatography, LC? So LC separation is achieved on the basis of molecular polarity by partitioning between a liquid mobile phase and a liquid film absorbed on the solid support material. So, well, in this case, that's actually a working principle for LC, liquid chromatography. You have a mobile phase. It is not necessary to be water. It could be other solvent. It could be other solvent. But in the case of liquid chromatography, the driving force or the mobile phase is the liquid. Liquid. It could be water or it could be organic solvent. Okay. Okay, so we'll be introducing ion chromatography in the very last parts of this chapter. But before we get in there are actually a few commonly used terms for chromatogram. So the term chromatogram， 大家背单字时间又到了what is chromatogram？ chromatogram 程析图谱吗？还是什么？好 ，chromatogram is a plot like this， OK， 所以它叫程析图谱啊，如果没有记错的话。Anyway， the chromatogram is a plot like this. So in this plot, the x-axis is the time, and the y-axis is the signal generated from your instruments. Okay, so later on, we use like different. I will introduce different detectors. So the mechanism for generating a signal would be different, like from machine to machine. But overall speaking, the x-axis is the time. So what does time zero mean? How do we define time zero in a chromatogram? Okay, usually we define time zero as the timing you inject your sample into a machine. Okay, so in a chromatogram, we define time zero, the timing when you inject the sample, right? And the y-axis is the detector signal. And let's use HPLC as an example. Let's use HPLC as an example. And we can so HPLC. Right. So let's look at this animation. Well, this is the column or column. So in a HPLC column, the blue dot, the blue color parts represent the solid material. The column is packed with a solid material, which is the stationary phase. Okay, and here the green dots represents your target compound, the target compound in your sample. Okay, so and following a column, usually we'll have a detector. So in this case, I use UV-Vis spectrometer as a detector. So I use it a lot. So the for UV-Vis spectrometer, you have external light source, okay, and when the light is passing through the cell, if you have like target analytes which is capable of absorbing the wavelengths, you see attenuation in terms of the light intensity. Okay, so the figure, the y-axis is the absorbance, which is defined by minus log P over P naught. Okay, that makes sense. And the y-axis is the T, and we define the time we inject a sample as a time zero. So try to imagine that, at time t0, at t0, there's nothing in the cell, right? So the absorbance should be pretty low because there's nothing in the detector chamber. Okay. So over time, the mobile phase is pushing the compounds like towards to the right-hand side. Also, try to imagine that you have a stream of liquids like continuously pushing the whole thing, moving forwards. So at time 30 seconds, well, still nothing coming out, and so the signal, the absorbance remain at a low level. And it is until, at some points, when you start have something coming out of the column and get detected by the detector. Okay, in this case, some of the target analytes, come out from a column, and you start seeing an increase in terms of the absorbance. So the next moment, and then the next moments, the next moments. Okay, and by the time that's every single compound, pass through the detector, you see the absorbance resume to a relatively low level. Okay, so this is how we generate a chromatogram from HPLC UV. Okay, and imagine that in the second scenario, instead of having only single compound in the sample, now you have more than you have two compounds. Okay, and then we inject the samples into the machine. So, over time, you'll see that the red compounds definitely has higher affinity with the mobile phase, or you can say that the red color compound has low affinity with the stationary phase. Either way, okay. So then, by the time of 180 seconds, you start seeing something coming out of the column and get detected by the detector, and that's when you see the first peak. Okay, and then moving on, the second compound get detected. So that's how we get a chromatogram. Okay, so does it make sense? Okay, so this is actually a typical chromatogram for gas chromatography or liquid chromatography. So in this case, how many peaks do you see? Apparently, there are 3 peaks. Okay, but something we want to keep in mind is that, in terms of chromatography, usually we'll see a peak appear at a relatively short time. Okay, for example, here, this one. And we call this one a retentive peak. So what does it mean exactly? So a retentive peak means the signal is from the compound in your mixture that are not retainable by the stationary phase. Okay. In the case of gas chromatography, let's say you have a sample, gaseous sample, and you inject it into the machine. So apart from the target analytes, what are there in your sample? Apart from your target analytes and other organic compounds, what is the main ingredient or what is the main components in a gaseous sample? Probably nitrogen and oxygen, right? Okay, and nitrogen, oxygen, those compounds, they are pretty small. They are not able to interact with the surface of your column. So it ends up getting eluted very quickly. So we call this kind of compounds unretainable compounds. And this unretainable peak is actually from those compounds that has no intermolecular or little interaction with the stationary phase. Okay, and in the case of HPLC, if we are using organic solvent as the mobile phase, the unretened peak is actually from water. 所以我再解释一下哈，这个是一个蛮常见的分析图谱哈。那这个图谱通常会有几个 peak 在很前面就出现的。那很前面就出现代表什么意思啊？有 compound 完全不会就是被这个 column 给留，就是因为有这个作用力的方式，然后让它慢下来，它就是一下子就跑出来了。好，那这些 unretentable 我们叫做 unretentable compounds 或者 unretained peaks， 它们是从哪里来的呢？在gas chromatography 的 case 里面呢，它就是你气态样品里面一定会有这个空气嘛，空气就是氮气或者是氧气啊，那它们很小，它们不会跟这个 column 有任何的 interaction 或者很低的 interaction， 所以它们很快就跑出来了，然后被侦测到。好，那如果 HPLC 的话，水样的话，除了你要看的那些有机物质们或者是无机物质们，最多的东西应该就是水吧。好，那水很快的就流出来了，所以就会有一个水封，我们讲水封。Okay. So, if we take a closer look at these chromatogram, so at time Tm, we see a peak of unretained compounds. So may due to the response of air in gas chromatography or solvent in the case of liquid chromatography. Okay, so at time Ta, that's the first compound A, Tb is compound B. So the reason why I bring it up here is because there are some theories for chromatographies. Okay, so some features for a chromatogram. So, the generally speaking, we see some this kind of features. For compounds, they get eluted like very beginning. Usually, the shape of the peak would be relatively sharp. Okay, so this is one of the key features of chromatography. For peaks appear in the very beginning of the chromatogram, the shape tend to be sharper. And for compounds that got eluted very later, usually the shape is become broadening. And this is because of the random diffusion process in the column. So for those compounds that move fast, they are able to maintain the distribution in the column is like more compact. So when they got eluted at the end of the column, like the shape would be sharper. 所以在那个分析图谱里面，第一个要讲的特性就是分析图谱越晚跑出来的 compound， 它的 peak 会越丑。那你觉得这个可能没关系哦？没有啊，你越丑的话，你到时候在积分的时候，你在定量的时候就会越痛苦。所以不要觉得它没关系。Okay. So the drawback of getting a broadening like peak is, when it comes to a time you want to do integration of the peak area, because at the end of the day, when you want to do quantification of the compounds, we do integration for the peak area, and a broadened peak would make you some. Will bring you some trouble because when it comes to a time you want to integrate the peaks, it will become more difficult. Okay, so right, and typically, typical chromatogram for the peaks, they usually feature symmetric nature. symmetric means that if you cut it into half, it's like a mirror. Okay, so ideally speaking, a peak in a chromatogram, they usually feature the symmetrical nature. But in reality, if the column is aging, let's say you use it for a long time and become aged, the peak would become skewed. Skewed means 这个偏向某一边的，我们叫做 skewed。那通常会有一个拖一个长长的尾巴，叫做这个 skewed peak. So it happens when the column is aged. For example, you run it for a long time, and well, that's when you get some trouble for like integration. Okay, so I guess I'm gonna stop here, and I will upload the video on the system before next Thursday. So make sure you complete the videos on time, right? I'll see you 3 weeks from now. 3个礼拜后见，下礼拜、下下礼拜、下下礼拜。Okay. Please return like your midterm to me. Thank you.